Hello everyone. Okay, this video is a supportive video. Okay, this video is about internal kinetic energy. Yeah, I think in last video in elastic collision, I left a little tail. Oh, sorry, not this one. In that video, okay, wait a minute. In the internal kinetic energy video, I left a little tail. Okay, I left a little tail. The tail is uh, the kinetic energy of the system is equal to the kinetic energy of center of mass and plus the internal kinetic energy. And in this video, I say I didn't have time to prove this. So in this video, just supportive. I just do this proof because the proof is it's not difficult. Okay, so let's start with it. Okay, let's turn to the new page. Okay. So let's do this proof. This proof is very easy. First of all, let's think about if you have system of particles. Okay, what's the kinetic energy of system of particle? Okay, kinetic energy of the system of particle. The system of particle. Okay, so that means we now have a many particle system. So what's the kinetic energy in a many particle system? Okay, we just add the kinetic energy of each particle and add them together. Well, that's the kinetic energy of the system of particles. Just add the kinetic energy of it, add the kinetic energy of every particle together. Of every particle together. Okay, so from this definition, like the kinetic energy of the system of particle is equal to, yes, I mentioned alpha, 1/2, and the mass of each particle is m alpha, and the velocity of each particle, and velocity of each particle, n square. It's add the energy of each particle together. Okay, and this is simplified form, but because we want to extend this derivation to the more general case, for example, in 2D and 3D case, so we use a vector form. Okay, let's use a vector form. Okay, so it's involved some vector calculation. Okay, but it's not that difficult. So it's actually m alpha, and your magnitude of velocity vector of each particle, the magnitude of velocity vector of each particle, and then square. Okay, in vector format, that's the kinetic energy. Okay, this become the vector, the magnitude of each velocity vector and square. Okay, so this is a v square, and we just do a little. That's a small trick. Actually, not a trick. It's square. Okay, let's just modify this a little bit. M alpha. It's actually square. Okay, so square means the two vectors that doing a dot product to themselves. Yeah, the vector dot product to itself. Okay, so it becomes v alpha dot v alpha. Okay, that's a square, right? V alpha, the vector dot doing a dot product to itself, it becomes a square. Okay, it's magnitude square. Okay, so should I write this? A square is equal to a dot a. Okay, it's a vector calculation. Okay, so this dot is dot product. Okay, so let's first of all write down the vector form of the total kinetic energy of the system. Okay, and let's say we are dealing with the internal kinetic energy. So okay, for internal kinetic energy, we introduce a concept called center of mass frame, or called zero momentum frame. In that frame, the observer is moving along with the center of mass, or you can say the observer sitting on the center of mass. So the observer observe the different velocity from the laboratory frame. Okay, so when you're sitting on a center of mass, the velocity of a particle become the relative velocity between the center of mass and particle. Okay, so when you're sitting on the center of mass, the velocity of each particle will become the relative velocity to center of mass when you're sitting on the center of mass. Okay, so and what is the relative velocity of relative velocity? Relative velocity. So I use R. So for relative velocity of each particle. Okay, for a certain particle, and it's a vector now. So we are dealing with vector. Okay, and it's equal to the velocity of a vector of particle and minus the velocity vector of center of mass, right? Okay, so this is a relative velocity with respect to the center of mass. Okay, so and we do a little algebra work. Let's tell you the velocity vector of each particle is equal to the relative velocity. Okay, sorry, maybe I use this equal to the velocity vector of center of mass plus the relative velocity of each particle. Okay, so and we then put this back to into this equation, and then we can solve this problem. Okay, we can just do this proof very directly. Okay, so okay, what will we get? Okay, so it's equal, k is equal to summation alpha 1 over 2 m alpha. So let's replace the v alpha. So it will become center of mass of velocity of center of mass plus relative velocity of each particle and doing a dot product. So it's VCOM plus V R alpha. Okay. So, and then we just do a little dot product. Okay, dot product is actually not that difficult. So 1 over 2 m alpha. So we are doing a dot product. Okay, so the first term is v dot VCOM dot VCOM dot VCOM. And so, and then we have cross term VCOM dot relative velocity m, relative velocity dot with the center of mass, the velocity of center of mass, and this cross term are the same. So I just write it write it. So just add these two terms together, and these two terms are the same. So it's become 2 times the center of mass velocity vector, doing a dot product to the relative velocity vector. And the final part is the relative velocity or the relative velocity of each particle dot relative velocity of each particle. Okay, so and then we'll have 3 terms in there. So we have 3 terms. Let's write down these 3 terms specifically. Okay, the first term is here. Okay, so v dot v. Okay, it's the same vector. The vector doing the inner product to itself. It will become the magnitude square. Yeah, the magnitude square. So this will become VCOM and square. Okay, this is the first term. Okay, right now the second term, so it's 1 over 2. Okay, so it's 1 over 2 here, and here's 2, so you can cancel out. So we will have summation alpha, m alpha. So this term is VCOM dot V R alpha. And the last term, sorry, this is not addition, this should be plus. This should be plus. Okay, the last term is plus. What's the last term? So summation alpha, m alpha. Okay, it's 1 over 2 m alpha. So it's the same. The vector doing the dot product to itself is become the magnitude square. So it's v alpha r vector square. Okay. So let's look at each term. Okay, there's something happening each term. So let's see the first term. Okay, the first term, the summation alpha m alpha VCOM square. Actually, we can factor out this 1/2 and VCOM square, because the summation alpha is only doing the summation to the mass. So it has nothing to do with 1/2 and VCOM square. So we can factor it out, COM and square, and left the summation alpha m alpha. And summation alpha m alpha, that's the total mass of the system. Let's assume the total mass of system is capital M. So it's capital M times VCOM square. Okay, this is M, total mass. Total mass. Okay, total mass. Okay, so in the second term, let's look at the second term. The second term, the same thing. We only care about the summation alpha. So VCOM is nothing to do with the summation alpha. So we can factor it out. And it's summation alpha, M alpha, plus, and the V alpha. Okay. So that's the next problem is, what is this term? Actually, is the total momentum in the center of mass frame. Do you see that? This term is the total momentum in the center of mass frame, in the COM frame. Okay, because it's mass times velocity, right? So it's momentum is summation O, and it's in the center of mass frame, because right now the velocity is a relative velocity and it's relative to the center of mass. So it's a total momentum in the center of mass frame. And in the previous video, I said check one thing by yourself. Check what? Check the total momentum in the center of mass frame is 0. Okay, but previously we just have this is two particle problem. But anyway, two particle is also a many particle system. Two particles is also a many particle system. So in the previous video, I said check yourself. It's okay. So the total momentum in the center of mass frame is 0. Okay, so it's m times v m relative velocity and capital M times v capital N relative velocity, and add them together is 0. It's two particle system, but also tell you that the total momentum of the center of mass frame is 0. So we use this conclusion here. Okay, maybe the proof is not very rigorously, but yeah, but that's most easy way to prove this. Okay, so okay, so this term is 0. Okay, this value is 0. Okay, so this value is 0. So this totally will become 0. Okay, and so what's the last term? The last term is, okay, it looks like the kinetic energy. Okay, so that's like kinetic energy. That's the kinetic energy in the center of mass frame. Okay, do you see that? Previously, we used this formula to calculate the internal kinetic energy, right? We just just calculate the kinetic energy in the center of mass frame. Okay, and we also finally give a name. That's called internal kinetic energy. Okay, so this is also called internal kinetic energy. Okay, and yeah, I forgot what's the first term. This is the total mass times the velocity. Total mass times the velocity of center of mass square. So this is kinetic energy of center of mass. So we add these three terms together. So we have finally we'll get this K is equal to 1/2 capital M VCOM square and plus summation alpha 1/2 M alpha VR alpha square. So this is kinetic energy of center of mass. This is kinetic energy of center of mass. And the second term is the internal kinetic energy. That's the kinetic energy in the center of mass frame. Okay, so this is a very short proof. It just show you this equation is correct. Okay, yeah, and I found the textbook also show this equation, right? It's on page something equation 9.9. That sounds like equation 9.9. So okay, so that's just, but the textbook doesn't show the proof. Yeah, it shows a little proof, but in the description, in a paragraph description, but that's not really obvious. That's not very obvious proof. Okay, so here's the proof for this equation with a stop video, and see you in the next video. Bye bye. Gone 15 minutes.